A sardine school folds through blue water, keeping thousands of bodies close enough to behave like one nervous silver animal. Then a shark approaches, and the part worth watching is not the mouth, but the absurdly long blade trailing behind it. The pelagic thresher does not simply chase one fish until somebody gets tired, it attacks the architecture of the whole school. Its first move looks almost restrained, a level approach, a brief adjustment of the fins, and a body beginning to pitch. The restraint is temporary, because the tail then travels over the shark in a fast arc aimed through the crowded prey. Researchers skimmed this sequence in the wild, where a suspicion repeated by fishers became a behavior that could finally be measured. The result is one of the ocean's stranger engineering solutions, a predator carrying a long-range striking surface behind its teeth. Calling that tail decorative would be like calling a trebuchet, an interesting piece of carpentry, technically possible but strategically unhelpful. The real question is how a swimming animal can stop, rotate, accelerate, strike, and recover without turning itself into underwater luggage. To answer it, we have to slow the hunt down and follow 4 connected phases from approach to the final turn back. Stories about thresher sharks using their tails had circulated for years, but a plausible story is not yet a measured hunting sequence. At Pescador Island in the Philippines, underwater observers recorded 61 encounters and analyzed 25 clear pelagic thresher hunting events. Of those recorded hunts, 22 were overhead tail slaps, while 3 captured a slower sideways form of the behavior. That distinction matters because the dramatic overhead strike was not a single lucky camera angle dressed up as a universal rule. The team could compare repeated events, track anatomical landmarks, time phases, and separate successful attacks from unsuccessful ones. 6 overhead videos were excluded from detailed analysis when sardines obscured the shark, timing was unclear, or the camera was too distant. That is less cinematic than pretending every frame is perfect, but it is exactly how a reliable result survives bad underwater visibility. A second study on common threshers in Southern California recorded 34 feeding events, all initiated with the upper tail lobe. 2 thresher species, 2 field settings, and different strike orientations point toward a tail that is part of feeding, not merely propulsion. The footage does not show a magic trick, it shows a repeatable sequence with failures, recoveries, and occasionally several sardines collected. The overhead hunt begins with preparation, and preparation is where the shark quietly rearranges the physics of its own body. It lunges toward the bait ball in a roughly horizontal plane, but the lunge itself was not the prey capture event in the analyzed sequence. Near the school, the shark draws its pectoral fins inward, changing pitch and allowing the rear of the body to rise rapidly. The maneuver also stalls the forward approach, which keeps the animal near the target instead of simply driving through and scattering it. Immediately afterward, the pectoral fins rotate laterally to counter momentum while the tail base begins its powerful ventral to dorsal motion. In other words, the shark briefly turns swimming hardware into braking, aiming, and launch control, which feels greedy but appears effective. The study divided each hunt into preparation, strike, wind down recovery, and prey collection because each phase has a different mechanical job. Preparation lasted longer than the other phases, consistent with the time needed to position the body and load the sweeping movement. The mean preparation time was 1.04 seconds, short for us, but spacious enough for a sardine already committed to the school. Once the shark has changed pitch and checked its forward motion, the long upper tail lobe has room to accelerate over the body. The strike is driven from the caudal peduncle, the muscular narrow region where the body hands motion into the tail. From there, the elongated upper lobe sweeps forward in an arc that can terminate above the shark's own snout. Across 16 analyzed sharks, the tail tip's mean speed over the body was 14.03 meters per second, about 5 kilometers per hour. The fastest measured slap averaged 21.82 meters per second, about 6 kilometers per hour, but that was an extreme, not every strike. Speed rose in 2 phases and peaked near the apex of the arc before falling as the tail approached its terminal position. That curved path lets the shark send a large striking surface through several tightly packed targets rather than aiming its jaws at one. The tail can make direct contact, while effects around the fin remain consistent with the pressure explanation rather than a measured certainty. Small bubbles appeared near the apex during many successful overhead events, a sign consistent with dissolved gas leaving the water locally. The paper treats the mechanism cautiously. The bubbles are consistent with rapid pressure change that may release dissolved gas, not supernatural claims. Water is doing what water does under a violent pressure gradient, which is impressive enough without promoting the shark to wizard. A schooling fish gains protection because confusion, shared vigilance, and many possible targets can make an individual difficult to isolate. The Thresher changes that calculation by attacking the dense arrangement itself, where one sweep can affect more than one prey item. After a successful overhead slap, the shark winds the body back toward ordinary swimming posture and turns around toward the damaged school. Researchers saw successful sharks collect dead or stunned sardines, sometimes taking several fish after a single completed striking sequence. Among successful recorded events, the mean number consumed was 60 sardines, with observed outcomes ranging from 2 to 7. Predation attempts were successful roughly 1/3 of the time, so this is not an automatic seafood dispenser attached to a shark. Failures are important because they show the behavior has costs and constraints rather than being a perfect weapon activated on command. The long preparation, brief strike, recovery, and return make sense as one integrated strategy only when prey arrive in a dense school. Against scattered fish, that enormous sweep would have fewer targets. Against a bait ball, the geometry finally pays its rent. Evolution did not give the shark a sword so much as a moving net with no mesh, followed by a very selective cleanup crew of one. The filmed pelagic threshers also used sideways slaps, but those recorded events were rarer and followed successful overhead attacks. In those observations, the sideways motion targeted individual fish already swimming erratically and possibly injured by the first strike. That makes the lateral slap look more like finishing work than the main method for opening an intact bait ball. Common threshers in the Southern California study showed lateral tail strikes while feeding on tethered prey, broadening the family comparison. The species and experimental settings differ, so Atlas should not collapse every thresher hunt into one rigid choreography. Nor should simultaneous observations of multiple sharks be promoted into cooperative hunting when the original field reports were anecdotal. The pelagic thresher study explicitly treated social or cooperative interpretations with caution because those observations were not verified. This is where documentary restraint helps. Uncertainty is not a hole in the story, but a boundary around what the camera genuinely established. We know the tail participates in feeding across more than one thresher species. The exact repertoire depends on species, prey, and situation. A good explanation leaves that variation intact instead of ironing 3 remarkable sharks into one convenient animated diagram. Threshers are immediately recognizable because the upper lobe of the caudal fin approaches the length of the body in this shark family. Recent anatomical work on common threshers found regional changes in vertebral morphology consistent with flexibility and load along the tail. That anatomy does not prove every detail of the pelagic strike, but it helps frame the tail as a specialized moving structure. Pectoral fins, body pitch, the peduncle, vertebral column, and upper lobe all participate. This is not a loose whip bolted onto a normal shark. The same animal still has to cruise efficiently, maneuver, pursue prey, recover after a strike, and avoid injuring itself in the process. Its solution is coordinated timing, slow enough to aim, fast enough to strike, and controlled enough to return to swimming immediately afterward. Pelagic threshers also visit cleaning stations at coastal seamounts where they change behavior to interact with cleaner fishes. Those calmer circles are a useful visual counterpoint. The famous tail belongs to an oceanic animal with more than one behavioral problem to solve. Hunting footage reveals the weapon, while cleaning station research reveals an animal managing parasites, habitat, risk, and routine maintenance. Even a shark carrying a trebuchet apparently needs an appointment for somebody smaller to inspect the machinery. So, the mystery is not simply whether a thresher shark hits fish with its tail. Repeated field video settled that question. The deeper answer is a sequence. Approach the school, alter pitch and stall, accelerate the upper lobe, then recover and collect prey. Each phase creates the conditions for the next, turning an inconveniently long tail into a controlled hunting system. The bait ball matters because density changes the economics, allowing one arc to disturb or strike several possible meals. The measurements matter because they replace a fisherman's story with timing, trajectory, exclusions, failures, and speeds tied to visible events. The uncertainty matters too. Bubbles are consistent with pressure effects, while social behavior and variation among thresher species remain bounded claims. What remains is still extraordinary. A shark can break its approach and send the far end of its body forward past its own head. Then, if the strike worked, it turns back through the silver confusion and collects the fish the tail left behind. The mouth finishes the meal, but the hunt was decided several body lengths earlier by the part of the shark swimming in last place. That is the pelagic thresher's trick. Not a tail that follows the predator, but a predator organized around where its tail can go next.